Welcome to a new test and teardown video. This time it's another Radiometer product. An oscilloscope called OSG32. And I believe that one is the serial number 1703. I'm not able to look up this one. I don't have any manuals or schematics or anything like that, but I of course plan to go and visit my friends at Radiometer, so I will probably be able to find it somewhere in the basement. But let's see. If and when I find any kind of manuals and information, I will put a link in my description. So that is where I can update this. And I already released two other videos about old Radiometer oscilloscopes, the 41 and the 42 model, and they are from 1950, start of 1950. So it's quite clear this one is a lot older. So I expect 1940 something. It's 22.5 kilos, so it's not super easy to lift. It's 45 centimeters deep, including the knobs, 26 centimeters wide, and it's 37 centimeters high. Everything here is written in Danish, so they didn't really expect this to be an export product. This means amplification, omskifter, that is a switch. So that will be some different modes of the Y channel. It's the same with the X, and you need to figure out what that means. And styrke is strength. So that's probably a level, and fine adjustments, light, focus. This is not exactly what you expect, but this is speed and length. And what else have we got? Yes, so this is of course the Y and the X position I would expect. And here it says connected or disconnected. How cool is that? So I better open and inspect and have a little look about its state. Oh, I also now in this light I can see something here is missing. Look at that. We got some screws here and they should clearly hold. Maybe this is a shadow for the roof mounted light or something like that, and that seems to be missing. Look at the cracked paint job as well. We got these access plates here at the sides. So I need to unscrew these and then get in. That will be deflection connectors. And those banana connectors, they also consist of a switch. So when you put in a banana, you disconnect the internal amplifier to the deflection plates. And this way you can access the full deflection plates with an external amplifier. So let's look a little bit inside. This is the right side. Then there is a lot of empty space up here on the right side. We got only one little red Phillips tube. It could be the EF6 or some other similar. I will pull this out later and make a little tube list if I can get to all of them and maybe read the whatever it is. Here I get some little flashlight so we can see that beauty. This is probably in the high voltage. I don't know exactly what that is doing yet. I'm also hunting down capacitors or anything with a date or year code on them. This particular model here, they sometimes have the dating written on that label, but that is of course pointing towards the rear side, which is a little bit annoying. We got in here a little shielded, extra shielded plate, and remember there's also a nice shielded plate up here, so they're really trying to avoid hum into the CRT section. And here we got two rather large transformers. I don't know, I cannot get light in there. And then there is one very, very beautiful old tube right there. All those capacitors. They say made in Denmark, but no year code on the Hellesen's capacitors. This one I've seen a lot before in old Radiometer, and they also sometimes have a year code on that capacitor. This I cannot see. And here is the left side of the unit. We got some really big ones. I think these are the same. And there's another tube up there. This could be one of those. Ooh, we got some melted capacitors. Not so good. See those trimmer capacitors? That will be to trim the bandwidth in this switch on the front. All that leakage here is probably from melted components. Ooh, and that capacitor here is about to explode. And again, I really don't see any year codes. Filter inductor. And that is one really, really nice. What the heck is that? Nothing is written on this tube, but it's definitely super, super old. If I go find, I will find the tube list or somehow make that one. We got some capacitors hanging around here in long leads like that. Really not good for vibration, but you can't get a lot of vibration into this thing because it's so heavy. Ooh, here we got a complete meltdown. Look at that. Something just splattered, melted all over the place. Oh, no. So something here. Where did that come from? Oh, it came from this. There's a capacitor. And this is why visual inspection is super important. And it's not super easy to get in there. I'm super sad that, yeah, see, a melted capacitor. It's difficult to video this. Well, I think you get the point. Very important to do a deep going visual inspection, because if you just plug in old stuff like this, it's just going to blow up on you and you're going to get smoke out of everything. And then the repair is going to be a million times worse and you're just going to give up real fast. Don't you just love it when you guess right? Give 6. I just came home from Radiometer. I went through their cellar and I found all the oscilloscope manuals of the really old oscilloscopes. Yeah, and some other manuals. And so now I will scan all the schematics and manuals for all the real old oscilloscopes. But this one I'm working with is called OSG32. And here is the original material for this one. So, what kind of luck is that? Of course, I also scored a huge box of all the other goody things, and I will scan this and put it online for free. Look what I also found. I found their own OSG32 in the museum. Their OSG32 is much, much younger compared to mine on the left. And this also means that the schematics, they are of course for the much younger model, and I do find a little bit of differences in my much older unit. Here is a few pages from the Danish version of OSG32 manual. As you can see, the fire marks on the top right corner, and that is actually not only this manual but many of the old manuals I found. And yeah, there was a fire in 1943. The Radiometer factory was actually sabotaged by the resistance 1st of August 1943. So that is why we have these fire marks. So it's a quite impressive part of the history. Somebody, of course, did not want somebody else to get access to any kind of cool technology that could be used. So here is the schematic for OSG32. This is the D version, so this means it is a little bit younger than the version I got, but we can enjoy this cool schematic. And let's zoom in on the top left corner. This is where we find the vertical amplifier. So the vertical amplifier consists of 3 tubes. The first one we see here in the schematic, they call this the EF42, and that is of course a tiny little tube, and definitely not the tube I got in my unit. The one I got in my unit looks much more like an EF50 or something like that. I really don't know for sure what exactly it is, but that is the main difference between my unit and the schematics. After that tube, we got 2 EBL1 tubes, and they are of course driving the deflection, vertical deflection, in a balanced mode. The fun thing is, as far as I can see, the input of the first one is inverted, and then the next one drives also the deflection. So it looks a little bit like they're not perfectly in differential mode. I mean, one of the of the deflection plates will have more output compared to the other one, but they didn't put this decoupling cathode resistor on the last one, so maybe it is a lower, much lower gain, but definitely it is inverting and it is also gaining. But anyway, so that is the deflection system. If we look at the bottom left corner of the schematic, we see 2 other tubes. The EC50 tube is a beautiful gas-filled tube, and this one is filled with I can't really remember if it is helium or neon or a mixture of some gases like that, and not super vacuum like in all other tubes, and that is to give it much more aggressive reaction. So it is like a trigger tube, and this is definitely for the sweep system to get you back and reset the sweep, so it's going slowly to the right and fast to the left of the sweep. So this is normally why you see those tubes. The bottom left is just a normal EF6, nothing fancy smancy about that one. This is of course just the sweep amplifier. Then we can zoom in here on the CRT, And it is a little bit interesting to see the schematic symbol of the CRT. I kind of like the way that they drawn the CRT, so you can easily see all the different plates and how everything is inside the CRT, and this way easier understand what is going on. You can also see one side of the horizontal, the sweep. The deflection plate is directly connected to ground. So ground is actually your anode potential of the CRT, and it is only sweeping on the left. I think it is actually the left, not the right as is shown here on the schematic, but that is not super important which one of the deflection plates it is, so never mind about that. But the point is that it is AC signal that goes to the sweep system, and the center of that point goes, of course, to X position potentiometer. And there you have the right part of the CRT, that will be the focus and the brightness and the filament, of course. And let's go a little bit more to the right. Here you have the second transformer of the circuit. We have in this scope we have two huge transformers. One is for the high voltage and some filaments, and the other one is the lower voltage, the normal anode voltage for the rest of the amplifier tubes. Okay, so this 1876 rectifier tube is probably the most beautiful tube inside this oscilloscope. I'm so happy just to sit and look at this tube. It is that beautiful, a rectifier tube. It is a directly heated, so the filament is actually the cathode. This is also visible by looking at the schematic symbol, and there you have it, the position of the Y. They call this forskydning, that is displacement, so this is position, and X position is just a normal potentiometer across the high voltage. And as you see here, the center of this is actually ground, and this is why using the current in the high voltage system you get voltage over those resistors, and this is why you have a little bit positive on one side and a little bit negative on the other side, and this is how you get a positive and a negative voltage in relationship to the deflection plates. At the upper right corner we see the other transformer with the voltage selector. Here the voltage mains input voltage selector goes, of course, to both of the transformers in parallel, and this is the one that generates the high voltage for all the rest of the tubes. The high voltage isn't really regulated or anything like that. You don't see any voltage regulators, so that means depending on your mains supply, one day it's a little bit higher, one day it's a little bit lower, you get more or less deflection, you get more or less brightness, you get more or less of everything. So that is just how it was in the very early oscilloscopes. We see some filter chokes in between all the different capacitors, quite a lot of capacitors in series with the high voltage system here. And let's look at this connection block from the top to the bottom part of the oscilloscope. They call this node 2, and there is of course also one at the bottom. This is how you can disconnect the top and the bottom part of the oscilloscope, and they nicely named those blocks some different names, letters and numbers, and this is how I can navigate around this oscilloscope and figuring out the different voltages and whatever is going on in this one. So here's my little tube collection from this oscilloscope. I'm still checking whatever it is we got and all that, and this is the one that I'm not super sure is in fact the EF50, but what can it really be? And I've of course double checked here, there's no reading or writing or indication or anything like that. There's a little code down here, it says 55 L1. Well, that is more or less all there is to it. All the different tubes, this style, they got more or less the same pinout, so that is not going to help me. I can, however, say that a lot of other radiometer equipment that age, I did find EF50s in them. So, and that is actually the only one that I found that looks like this. So that is why I go with this one. And here is this EC50 gas-filled Teardown or tube, the trigger tube for the sweep. Beautiful tube indeed. And this one is also a very, very nice rectifier tube. It's the EZ23, and they are cooled in a really cute way. I don't know how well I can show this, but those little spirals there, they're actually little coolers. And there's a little piece of glass in this one, by the way, a little loose piece of glass. But this one is definitely the top of the collection, if you ask me. I really love this. It is so, so beautiful. Also really, really big. See, there's a thin wire in there that goes through the glass down there. So, I mean, it's just built in a really, really special way. Also because this one is a very high voltage rectifier. It handles a couple of 1,000 volts. It's not so beautiful from this side because of this silver, but in here it's beautiful. Yeah, those are not super interesting. This one is completely covered, so we can't see anything. And also the EBL ones, you can't see anything through these. They covered them from the inside. I actually don't know why they did this. There's a tiny little hole up here, so unfortunately we can't see anything inside these. So I took out, of course, all the tubes so I could clean and inspect all the sockets. And we can also see this is the time base setting. And obviously this is where we find the time base valves. And we do see a little bit of leakage, all over on the bottom. And I think this comes from something up there. I'm still trying to figure out exactly what caused that one. All those capacitors, they look nice and fine. And down here, the mains entry, the mains cable was completely falling apart. And this is a problem with this type of isolator in the cables. This type of plastic kind of falls apart when you move around. This is, we can probably see both of the transformers in here if we're a little bit lucky. And they added an extra shield for the magnetics. I don't exactly understand why, but because there is another shield wall here and there's another shield around the CRT. So maybe they don't want this hum to go into the vertical amplifier that is all the way over there. But we have the filter chokes, and there you have it. This is the, we can call this the low voltage rectifier tube, and there will be all the capacitors for the 300 volts, and we have a lot more down here as well for the 300 volts. No, those two big ones down there, that will be for the high voltage, but we also have some more capacitors in here as well for this. And we got a wire that was falling off. It was kind of sticking halfway out here. So I removed this little protection to have a little look. And this is the parts that I call, or they call node 2 in the schematic. And here you can see they are nicely marked with some letters and some numbers. And this really helped me to figure out this is number 5, and number 5 is connected to all the different capacitors. So this wire here actually goes up here, and you can, if you look carefully, you can maybe see the soldering where it fell off. So I need to solder this, but again, when I move around with this one, it completely cracks, and this is exactly like the mains cable. I don't see any of these capacitor leaked. So this is the left side of the oscilloscope with all the tubes taken out, and I will of course try and zoom in on the most difficult part first, and this is my vertical input amplifier, and I found this tube in here, and I believe this is EF50, but that is just a guess, a qualified guess of course. And what you see here, that will be two 1000 microfarad capacitors, and they handle gain in this first stage, is that one, and this second stage, that one. So this is a cathode decoupling capacitor, and as you see here, it's just located out here because this is where you have space, and they didn't really find space in here where this tube is that uses this capacitor. So that's a little bit funny. In this section here, we also find this inductor right here. So this inductor is in the anode system together with some capacitors and resistors, and that is doing frequency compensation. The output of this amplifier goes to this connector here. This connector goes on the top of the EBL1 tube. And that is because this top here is actually the grid input to this tube. And so that is the input to the tube, and the output here is at the bottom. And it's the same for the next one, of course, its input is here. So I think this explains a little bit about what is going on here. And look at that leakage right there. I still don't know exactly where that is coming from, but I see a little bit of burned something right there. And then it's probably coming from that one. So maybe this capacitor leaked. But this is a low voltage capacitor, and it is located in a low voltage cathode system, so I'm really not worried too much about if it's shorted or not working or anything like that. If it is shorted, that means this tube here will run at maximum current, so I will slowly power it up and measure the voltage on this one. So they isolated this capacitor because this one is not grounded, but the next one is. But there's only a few volts here, so it's not a big deal. Just in case I blow something up, let's take a little picture of this assembled with everything in here. You never know what's going to happen. So this is the first power on test. Let's dim the light a little bit and see if there's anything going on. I am of course going to crank up the power real nice and slow. I did check a little bit in the manual. They say about 100 watts. So this is 17 volts. Let's just check. The mains switch is working. So this is on. So I'm monitoring the normal anode supply for all the low voltage tubes. So I guess about 300-400 volts on this one. This is the cathode supply, and we should expect about -700-800 or something like that on this one. And the high voltages, they will of course only come when the rectifier tubes, they warm up. So at the beginning, we'll see absolutely nothing. So this is 60 volts, and it's using 8 watts. And of course, since the filaments, they're ice cold in the two rectifier tubes, we get absolutely nothing. So now I will just slowly crank up the voltage, and then we'll see every time I put it up a little bit, I see the power consumption rise. And that is of course because it's warming up everything. And see, this is a direct heated rectifier, and it starts to get a little bit warm. So we get the first emission on the cathode supply. Of course, that will be 135 volts because I have a high voltage probe on this high voltage. So 1 volt is 1000 volt on that one. So we're getting up with the high voltage, and we are now at 120 volts, and it's using 17 watts. So I'll just continue real slow. So we are now, see, now we see some voltage getting up. And let's just keep it there for a little while and see if the voltage will get up. It's using 42 watts. And of course now, this is okay. Yeah, let's try and go up higher. Only one volt on the high volts, but suddenly this one is gonna sky rise. We don't have any kind of high voltage. It's using 90 watts here at 200. And this is a problem. We don't have any high voltage going on here. We have 700 almost on the high voltage. And of course you don't see, oh, what is that? Well, yeah, look at that. There is actually a beam and focus is responding, but we have a voltage missing here. So there's something I need to worry about. And power consumption is of course about 100 watts already. So I will need to look at this rectifier, and it also smells a little bit funny. So I'll get my thermal camera and see where is all my high voltage going. This is real interesting. Here is the 400 volt system. And remember, I earlier talked about those wires for the 2 capacitors. So I think those goes probably to this one, and those 2 wires goes to this one. But anyway, there are collected, all 4 parts of these 2 capacitors goes to this one point, and that is called 3. So this is the super clean voltage, but this capacitor is shorted. So there was probably a reason why they disconnected it, and because it's difficult to replace and all that. So they just disconnected this one, and now the scope is probably working. At least this is what I will try and measure. And the wire is also falling apart. By the way, let's see this capacitor here. See, very close to a short. And if I take the next one here, let's see what it says here on the meter. See, and then it goes like that. So this shows up as a capacitor being charged, right? And that is much more normal. So let's try again using the disconnected capacitors and see if we get any high voltage for the tubes. There's no need for me to monitor the cathode voltage because that one we know is of course working. So we can just dial up the voltage all the way to 200 because that was good. And we should definitely start to see some look at that, it is getting higher and higher. And here is 210 volts, and it's using 105 5. We have position here is working. Not much position of the other one. This reveals we have a problem with this system. Focus, light. Is at maximum. Our supply is still only 148 volts, so that explains why this position here is not working. Yeah, I better turn it off. And then it gets much better in focus. What the heck is going on with this one? So there's a lot of funny stuff going on, but at least I got a beam. I got a little bit of something. I'm actually a little bit happy that we got that much and not big flames and smokes and all sorts of funky things. This is a lot better. But where is all my high voltage? I'm still having a big fight with this unit. All my 300 volts is just completely overloaded, and there are actually a few things that uses quite a lot of power, and that is why. So first I added a little bit of black paint here on the 2 first capacitors, and they get warm. I give this unit 100 volt DC. I removed this rectifier tube in there and then put it in 100 volts, and then after a little while I see those 2 capacitors get warm. And of course I don't power up anything else, so I got ice cold filaments on all the tubes. So that means my 300 volts should of course use 0 current, right? But those 2 get warm, and all the series resistors on all the different capacitors, they also get warm and drop quite a lot of voltage. So that's also funny. So what else is using power? I need to figure out that next. But first, I want to try and take out these. It's not that easy to do, because you need to remove everything here, and those screws here, they comes from the inside. This you can't remove. And by the way, this is the high voltage, the cathode supply. And look underneath, we got some resistors right there, and they're supposed to be 0.1 meg or something. One of them is called 0.1 meg, but we got 2 resistors in series, and it's funny, it's mounted underneath this rectifier tube, because this is actually the return path. So we got these 2 wires here, and they're connected to the filament, but also to one end of the high voltage. I don't know if that is easy to see, but there is actually 2 wires on the middle one here. I don't know, but we got 2 wires on that one, so that will be filament and high voltage. The other end of the high voltage is here, so that wire goes here. It's not those 2 pins, this one and the other end where we have the wire coming out. Those 2 pins, they are not connected in the tube. They just use those 2 pins as a resistor holder. And this is a classic thing done on many of those sockets. And instead of putting little holders and screw this here or there and to have those things, they just use the remaining unconnected pins on tube sockets for holding parts. A classic design thing. So don't get confused about this. They all do this now and then. It is really some funny capacitors. Let me take the other one. So we got 2 wires coming out of the bottom, and that is of course the 2 individual capacitors, 16 plus 16, and the can is the negative. All right. And yeah, we see a little bit of leakage here. This is not that bad with this one. There's a little bit worse with this one, but it's not really that is the problem. It's not acids or something like that coming out of it. So let's just take those 2 capacitors. Let's put a voltmeter and let's put a power supply at the same time so we can see what is going on. Let me try and give this power supply some volts. It's actually more fun to be in amp mode because we can see the volts down here. So when I crank up the volts, let me just go straight up to 100. I want it to go to just 100 volts. And there you have it, 10 milliamps. So this is only 10K, but it's of course a lot worse if I give this more voltage, see? And then, and then it goes down. Like that. So it seems like there is some sort of a regeneration going on. So if I leave a voltage slowly rising and just waiting and waiting and waiting, then the leakage actually gets less and less and less. And I can't have like 10 milliamps per capacitor here in leakage because we got quite a lot of them, and it ends up eating more or less half of the available power. And on top of this, my rectifier tube is not as powerful as it used to be. So this is a classic thing with those rectifiers. This old one here, the internal resistance gets higher and higher, and it can deliver less and less current when it gets older and older. So that is just too bad. So this is what I will do just for now to see if I can carry on. So look at that. 22 micro, 2 of them. I don't know if you can see the size. I could put these up in the end of this one. I know this one goes to 500 volts, but we should only expect between 300 and something. It should definitely not get near the 400. And they are very useful to hold the unit so I can easier work on it. Perfect! So now I replaced all the capacitors with new modern teeny weeny sized capacitors, but they're actually a lot better. And I am back to the original value with 4 of them in parallel on voltage 3. So that is the same as 2 of those 2. Remember, one of them that was shorted, they just took out, right? So it's going to be real fun to see how this works out. And what do you know? It is now sweeping. And I can, of course, put it into focus. A little bit more brightness. Look at that. Nice, sharp. It's actually quite bright. So, okay, so far so good. And this is the, okay, we got a little bit of something here that's not perfectly. See, that is the different speeds. And then this is also how much, okay. And we got the speed, variable speed. And position here, I got a leakage in the coupling capacitor for X position, and this is why this is not working. And the fun thing with X position is it's actually working in direct mode, and in direct mode, you see, I can go positive and negative. That means this capacitor is now not bothering me, because it's actually, the input is just connected directly to the input connectors here. So how cool is that? I think I'm not going to make this video a million miles longer, but as you see here, we got a nice bright dot, and everything is now finally up and running. I'm using an external power supply for the high voltage because of this rectifier tube is not good. This one cannot deliver almost any current. So together with lead capacitors, of course, I had no voltage at all. And I think that will be it so far. I will just go and play around with this one the next couple of days. And it was a lot of fun to get this one up and running again. I hope you enjoyed the video, and I hope you learned a little bit about tube restoring, debugging, and all those kinds of things. And of course, as always, please like and subscribe and comment. See you. Bye bye.